Hello everyone, my name is Akshit and I am a PhD candidate at Indian Institute of Technology, Delhi. I would like to start by thanking Sintef for organizing the second edition of MRST Symposium. I am also thankful to my supervisor, Dr. Jyoti Phirani, for her guidance and the support. Now today I am going to talk about the capillary driven flow in layered petroleum reservoirs, and this, this work is a part of my PhD thesis. So the first question which comes to our mind is, what is the capillary driven flow? It means that the wetting fluid will imbibe into a porous medium to displace the non-wetting fluid without any external interference. That is, delta P is equal to 0 and PC is greater than 0. Means that free spontaneous imbibition occurs. Now, the next question is about the wettability. So wetting fluid and non-wetting fluid. So the tendency of a liquid to spread over the surface of a solid is an indication of the wetting characteristics of the liquid for the solid. The spreading tendency can be expressed more conveniently by measuring the angle of contact at the liquid solid surface. As you can see in this figure, different types of different fluids are spread on the solid. There are many actions of spontaneous imbibition. It is one of the main mechanisms in the oil recovery from fractured reservoirs. It is also useful for CO2 sequestration in saline aquifers and designing the microfluidic paper-based diagnostic devices. Now I will discuss about the theories and laws of fluid displacement in capillaries and porous media. Fluid flow in capillaries is governed by Washburn's law. Similarly, capillary-driven flow in homogeneous porous media also follows the Washburn's law, which states that the square of the length of imbibition is directly proportional to time. Washburn observed that the rise of fluid is faster in capillary of larger radius, as you can see in this figure. However, when two layers are studied in interaction with each other, Ashraf et al. Performed experiments to find out what happens when we have two layers in contact with each other and observed that the fluid goes faster in a smaller permeability layer because the capillary pressure is high in a smaller permeability layer. They also performed simulations to verify their results. The pressure profile in this graph shows that there is a sudden change of pressure at the interface. In this model, they assume that there is contact line displacement and no residual fluid is left behind during the imbibition process. So the front will have either 100% saturation of the invading fluid or there is no wetting fluid. So the assumption is valid for a small number of flow phenomena. And this is not the case in real geological porous medium. So to understand what happens in real porous medium, we should know that when the real scenario, the during displacement, there is a gradational change of saturation. Buckley and Leverett in 1942 gave a theory for fractional flow to estimate the oil recovery by water flooding. The wetting fluid is generally injected at a constant rate and the recovery as a function of time is calculated. Earlier studies on spontaneous imbibition presented an analytical solution for capillary dominated flow in one dimension by Schmidt et al. They use the fractional flow theory and the solution can be looked as a capillary analog to the classical Buckley-Leverett solution for viscous dominated flow. From the saturation profile for Buckley-Leverett solution, we can see that there is a sharp front. So the key difference in case of purely capillary flow is the diffusive nature, which gives rise to square root T dependence rather than a linear dependence in time. In this, we use the mass balance equation initially and solving the flow conditions. And to estimate the fractional flow of fluids, we consider the Darcy's law. The factors which are dominant in fluid flow due to capillary forces mainly include the porosity, permeability, capillary pressure, saturation curve, and relative permeability saturation curve. Now, coming to the problem statement that we are working on. So in this project, we want to study what will happen when we have two porous layers arranged parallelly to each other. And these layers have different properties. Because in a geological porous medium, sedimentary deposition happens in terms of layers at different geological types. As you can see that we can make different layers of varying properties such as permeability. However, we need to scale the properties, upscale the properties so that the properties remain constant throughout each layer, throughout the layer. Upscaling should happen taking into consideration how the flow is happening, so the flow behavior is captured accurately. At large scale also, like in a fractured porous medium, where the stratified layers can be meter thick, we want to understand how the flow is happening due to capillary force. So in this work, we want to study spontaneous imbibition for a layered porous media and make a simplified model to quickly see how the flow is happening without doing the simulation each time. So in this work, we use different parameters for which are important for this study. We use the porosity of 0.2 or you can say 20% and the permeability of 300 milli-Darcy for the three wettability cases as mentioned here. We took into consideration the different fluid properties such as water saturation, relative permeability, viscosities, and the other fitting parameters. We also looked at the mobility ratio, which is one of the important factors in oil recovery. This figure for wettability at pore scale shows that for water wet reservoirs, the water remains adhered to the smaller pores and oil remains in the free state. Now I will discuss about the 1D model that we constructed using the MRST simulator. We are studying the co-current displacement where the fluid flows in only one direction. We use the fully implicit scheme in the ad-blackoil and ad-core module to study the dynamics of capillary flow in porous media. We constructed a reservoir with the dimensions of 5 meter by 1 meter by 1 meter. We placed an additional grid cell of pore volume 10 times to that of the core at one end of the setup, which acts as the water tank. The boundary conditions in simulation are controlled by using the wells. We position one injector well in the water tank and one producer well at the other end of the core, with pressure of both the wells being the same to allow for the capillary driven flow. As shown in the saturation profile for different wettability states, the water saturation is plotted as a function of omega, which is the transformation variable. For a one layered or single layered homogeneous system, we compared the obtained saturation profiles from the simulation with the semi-analytical solution given by Schmidt et al. And we then also performed first, before verifying our results, we performed the grid sensitivity analysis for different grid sizes ranging from 100 to 600, and we found out that we have a good match at a grid size of 400 and we need not to increase the grid size further. In other words, we can say that each grid cell capturing a grid volume of about 0.25% can be sufficient to numerically model the spontaneous imbibition process. We also did the time step selection process for different time steps that we considered in the work. So we found out that even for about 600 seconds or you say the 10 minutes, the water the match is good with the 30 seconds time step also. So we can say that there is no much difference or no much effect of the larger time step up to 10 minutes. So it can capture the phenomena sufficiently. Now I will discuss about some of the results for capillary flow in homogeneous porous media for different wettability states. So this is first one is a strongly water wet condition. We input the arbitrary relative permeability saturation curve and capillary pressure saturation curve and use the viscosity ratio of 3 and the mobility ratio of 0.706. So we match our simulation results with the semi-analytical solution and we can see that there is a good match from the initial condition, but there is some deviation near the front. So this can be due to a fast movement in case of strongly water wet, which the numerical solution is not able to capture. And so this is done for 10 days and we can also see that QW naught is the water injection velocity at the inlet. This is calculated using C, which is generally used in simulation, and C tells how fast the spontaneous imbibition takes place. So now I will talk about the other condition of weakly water wet. So we use the different curves as input, and now here we have the viscosity ratio is 1 and mobility ratio is 0.6 to 5. So you can see from the saturation profile that there is a good match, or there is a close match with the semi-analytical solution for weakly water wet case. This is done consider, for a comparably larger number of days, and the saturation profile is plotted when the wetting fluid reaches near the producer end. The last case is for the mixed wet condition. So the input curves for two input curves, and the viscosity ratio is same as the mixed weakly water wet is 1, and mobility ratio is about 0.75. So in this case also we see a close match with the semi-analytical solution, and the it is done for about 5 years. The simulation was run for about 5 years, and we can say that the based on these three results, we can say that our simulator is validated for performing the spontaneous imbibition uh, simulations and to capture the process efficiently. Now I will discuss about the main topic, the capillary flow in two-layered porous media based on different permeability and different capillary pressure saturation curves. So first one is the based on different permeability. In this case study, we simulate a two-layered porous medium with each layer possessing distinct permeability properties. The yellow portion shows the water tank, which has the higher permeability as compared to the core. And for the core, we have two layers, and each layer has the first layer has a permeability of 100 millidarcy, and second layer has a permeability of 300 millidarcy. It is also important to note that all the other properties in both the layers remains consistent. We have based on the results of saturation as observed in the saturation profile, we have noticed that when the layers interact, the infiltration of wetting fluid occurs with more rapidly in layers with lower permeability, that is 100 millidarcy, and more slowly in layers with higher permeability, that is 300 millidarcy, in contrast to situations where the layers do not interact. Additionally, we have observed that the saturation profiles of both interacting layers are nearly identical, with any deviations only becoming noticeable near the front location. So we can also see the pressure profile, which reveals distinct characteristics for non-interacting and interacting layers. In the case of non-interacting layers, we observe that the pressure values are higher for a smaller permeability layer of 100 millidarcy, however, compared to the larger permeability layer. However, for interacting layers, there is an increase in pressure values for the larger permeability layer and decrease in pressure values for the smaller permeability layer. Interestingly, similar to the saturation profile, the pressure profile of both interacting layers exhibit a remarkable similarity. So this is done for the weakly water wet case data that we used. Now I will talk about the second case for based on different capillary pressure saturation curves. In this case study, we simulate a two-layered porous medium with each layer exhibiting the distinct capillary pressure saturation curves as illustrated in this figure. These curves vary depending on the exponents, which are the fitting parameters, while the endpoints of the curves remains consistent. It is important to note that all other properties in both the layers remain identical. And in this case also we use the weakly water wet porous media due to the number of days it takes to reach the producer end. So the exponent for PC1 curve is 0.2, 0.3 and PC2 curve is 0.5. So in non-interacting layers, the layer characterized by the PC2 curve exhibits leading front, whereas a layer with the PC1 curve displays a trailing front. However, when these two layers interact, a notable shift occurs. The layer originally associated with the PC1 curve, which lagged in the non-interacting scenario, experiences a sharp increase in its front, while the layer initially linked to PC2 curve, which led to the in the non-interacting which lead in the non-interacting scenario, sees a reduction in the length of its front. Consequently, in the case of interacting layers, the distance between the front locations of both layers significantly decreases. This can be clearly observed from the saturation profile. Also, it is important to note that in the interacting layer scenario, the pressure remains uniform in both the layers, indicating efficient fluid transfer between the layers. So, due to the positive time, I will not discuss the third case of different wettability cases. So, I will now summarize this key results and the study that we did. So, wettability, fluid properties, and petrophysical properties of the porous medium plays an important role in the imbibition dynamics. The interaction of between the layers can affect the imbibition pattern significantly. So in the interacting layers, we see a faster movement in layer which has a lagging front in homogeneous case. Similarly, we see a slower movement in layers which has a leading front in non-interacting homogeneous case. And the fluid front merges to same location for two-layered porous media for the cases that we used in this study. And the last one is the same pressure profile we observed for two layers, interacting layers in different for different curves, capillary pressure curves. So what is the scope of this feature work? So we want to find out the effect of the combination of the properties that we discussed along with the other properties, petrophysical properties such as porosity and relative permeability saturation curve. And we want to investigate their combined effect so to understand how the leading fluid layer changes. Thank you for listening. For any further discussion, please feel free to email to us. Thank you.